All right, so today we'll finish up section 4.2, and then if we finish that, tomorrow we'll be doing 4.3, and then that's it. All right, so that's what we did yesterday. Okay, we looked at graphic problems where the degree of the numerator was either equal to the denominator or smaller. Here's an example. So we might have done like x plus 1 over x squared minus 1. In fact, I think that was an exact problem in the homework, or very, very similar. But the degree in the bottom is, or the degree in the top is smaller than the bottom. We also did something like this. Say x squared plus 3 over x squared minus 5x. In a problem like that, the degrees are equal. When we found the EBM of this first one was 1 over x, and the EBM of the second one was basically x squared over x squared, which reduces to 1 over 1, which is just 1. So when these degrees were the same, our EBM didn't have an x in it. And there was a couple problems yesterday I asked you, tell me what happens to this fraction as x gets bigger and bigger, and there wasn't an x in the fraction. That happens when these exponents were the same. So now we're going to look at what happens if the degree in the numerator is greater than the denominator. So we'll look at graphing when the degree of the numerator is greater than the denominator. So what can happen when it's greater? Well, it depends on how much greater it is. If you had something like x cubed plus 2 divided by x squared, the degree in the top is greater, but it's only greater by 1. So that's not too bad. If you had a problem like x cubed minus 8x divided by x plus 1. So looking at this one, what's the degree in the top of that one? Yeah, 3. What's the degree in the bottom? 1. What's that a difference of? 2. That's a little more complicated than the one before it. The further apart these two exponents are, the harder it is to graph. So we're going to be focusing mainly on where the difference is either a 1 or a 2. Okay, we're not going to be doing anything higher than that by hand. When the degree in the top is bigger than the bottom, there's some new piece of information that we can find. This isn't something we've ever done. Well, this is not a name that I ever mentioned yesterday. EBA. We mentioned EBM. That's end behavior model. This is called an end behavior asymptote. So this type of problem applies in a situation like this. You have a polynomial in the top. You're going to divide by a polynomial in the bottom, and the degree in the top is bigger than the bottom. So generically, that's what you would have. So I'm going to just write that next to it. The degree of h of x is larger than g of x. If it wasn't, this would be the kind of problem we did yesterday, and this idea would not apply. All right, so let me say it like this. So to find the EDA, use division. When you use division, you're going to get a remainder. And does anybody remember what you call the thing you get when you do division? Like when you add two things, you get a sum. But when you you divide two things, you get a quotient. So to find the EVA, use division. The quotient is the EVA. The quotient is the EVA. So we've done division before. We never called the quotient the EVA, but that's just what we're calling it in this section. So it's nothing new. It's something you already learned how to do. Now remember, there's two types of division. We can do long division and we can do synthetic. As long as your denominator is of the form x minus a number, you can use synthetic division. If the denominator is more complicated than that, like x squared plus 6, well, then you got to go back to long division. Okay, so use synthetic division if you can, because that's easier. Okay, so the quotient is the EBA. And again, that stands for end behavior asymptote. That's the abbreviation I'm going to use. So let's try this one. This problem says find the quotient, find the remainder, and find the EBA. So it's 2x cubed minus 4x squared plus 3 divided by x minus 2. Okay, so first of all, is this a problem that I could use synthetic division on? Yes, because it's of the form x minus a number. Does anybody remember what number goes on the outside of that symbol? Yeah, 2. It's always the number that's after the minus sign. And then how about the numbers I'm going to put on the inside? Okay, hint, you're going to need 4 numbers. Lauren?
3, 2, negative 4, 0, and 3.
Okay. And to do synthetic division, bring down the first number, multiply, and then add it to the second column. So we're going to keep multiplying and adding. All right. What's 2 times 2? 4. Negative 4 plus 4 gives me 0. What's 2 times 0? And 0 plus 0? 0. And 2 times 0 again. And 3 plus 0? 3. Okay, does anyone remember what does that, what do those 4 numbers tell me? 2, 0, 0, and then a 3. Yeah?
It's pretty much telling you that you're left with just 2x and then the 3 is your remainder.
Okay, so my quotient is...
Or actually 2x squared.
Is 2x squared. And what did you say my remainder is?
3.
My remainder is 3. And what about my EDA?
3.
No, the EDA is not 3. Yep.
2x to the second.
2x to the second.
Oh!
The quotient is the EDA. Now, let's think about asymptotes for a second. Because this is a little weird here. What's one kind of asymptote we talked about yesterday? Yeah? Vertical. Okay. What's another kind we talked about yesterday? Yeah? Horizontal. And those are both examples of what? Like the shape of them. They're both lines. So far, we've talked about a graph getting closer and closer to something that's a straight line. This one's different. When you graph something that has a highest exponent of 2, what shape is that? Max? This is a parabola. So what's happening in this problem is there is an asymptote, but the asymptote is a curve. So you have a parabola as an asymptote, and your graph is getting closer and closer to that curve. So it might look something like this. It might come up, curve, and then get closer and closer and closer and closer as it keeps going. Okay? I'm not saying exactly what it looks like, but the idea is now your graph is getting closer to something that's curving, not something that's straight. We're not going to worry too much about sketching that. We're going to do it on the calculator. But you do have to know how to find this, not so much sketching. So any questions on that idea? The fact that now we're getting closer and closer to something that's curving, not something that's straight. Okay. So let's talk a little bit about EBA compared to EBM, what the difference is, and then we're going to take the problem we just did and we're going to prove, well, we're not going to prove, but we're going to use the calculator to highly suggest that this is the correct answer for the EBA for this problem. Okay, so there's a difference between the EBM and the EBA. They are not the same thing. The EBM is simpler. That's just the highest degree term in the top divided by the highest degree term in the bottom. That's what we did yesterday. The EBA is when you use long division or synthetic division and you get the quotient. That's a little more time consuming to find an EBA. EBA only applies when the degree in the top is larger. Since we didn't study degree in the top being larger yesterday, we never talked about the EBA yesterday. Now, if you take a given problem and you find the EBM and you find the EBA, it's like the problems we're doing today, I could do both. Yesterday we could only do EBM. But if I find both of them, they might end up being the same, or they might end up being different. If we go back and look at the problem we just did, there's your EBA, 2x squared. Let's find the EBM. What's the highest degree term in the top of that? Okay? 2x to the third. And what's the highest degree term in the bottom? More? X. And if you simplify that, you get 2x squared. That's the EBM. Well, it was also the EBA. So in this case, it came out the same. The only reason it came out the same is because both of these numbers came out to zeros. That's why. For these to both come out to zeros, that usually doesn't happen. The arithmetic just worked out perfect to make it happen. Yep.
Why is x the greatest value down there? Is that because that x would have to equal anything over 2? So obviously the negative 2 is greater than x.
Well, when you're talking about the highest degree term at the bottom, because technically this is how you write the bottom. The highest degree term is the term that has the highest exponent on the letter x.
So it's just implied that there's a...
Right. There technically is an x on this too, but it's an x to the 0 power, and anything to the 0 power is just the number 1. So this is really 2 times 1. So the degree of a constant number is 0. The degree of the x here is the 1 that's implied as an exponent. And the degree of this top one is a 3, because there's 3.
Which is why the variable is always the greatest, at least in this case, right?
Which is why the what is the greatest?
The variable, yeah.
I'm not sure what you mean by why the variable is the greatest.
Never mind. I understand. I'm trying to make it more complicated.
Okay. Okay, so sometimes the EBM and EBA are the same, sometimes they're different. Yesterday, this is what we dealt with. Degree of the numerator was always smaller than the denominator, and that resulted in straight line asymptotes. two types of straight line asymptotes. We did horizontal and we did vertical. And that's all that ever happened yesterday. If the degree of the numerator is not less than the denominator, like in the problems we're doing today, then we can end up with asymptotes that are curved. And this is where you have to look at the difference between the numerator and the denominator. The degree in the top is a 3, degree in the bottom is a 1. That's a difference of 2. That means your EDA is going to be a degree 2. The further apart the degree in the numerator and the denominator, the worse the EDA gets. Like if the degree in the top was a 5 and the degree in the bottom was a 1, the difference between a 5 and a 1 is a 4. So that means your EDA would have a degree 4. That's a more complicated EDA than even a parabola. Right? So we're going to be focusing on ones that generally are only one number or 2 numbers apart. And we're going to do a little bit more with that first problem right now. Yes?
So if the numerator is bigger by 1 degree, it's just a curve?
If the numerator is bigger, well, in this one it's bigger by 2.
Yeah, so what would it look like if it was bigger than 1?
So we're going to talk about that. It's a little bit simpler than this one we did, but it's a little more complicated than yesterday. Think of something that's a degree 1. What's the exponent on a degree 1? Well, if something is to the second degree, then that means it must have had an exponent of what? 2. So if something is a first degree, the exponent is a 1. So what does something look like if it's degree 1? One step simpler than a parabola. Yeah?
Straight line.
What kind of straight line? Because we studied straight lines yesterday, but this one is going to be a little different kind of line.
Is it going to be like angled?
It's going to be angled. So we're going to end up with asymptotes today when we do a degree 1 problem that the asymptote is a line, but it's going to be slanted. So it's a little bit simpler than a parabola, but not as simple as just being horizontal. And that's called a slant asymptote. We're gonna graph one of those by hand. All right, so what I want to do now is let's plug in the original problem from example 1. Or actually, I guess I said example 5 because this is the second part. So let's look back at the first example from today, which was example 5. Type that in. And then we're going to graph 2x squared and see if that looks like the asymptote. So I need the original problem first. So we have 2x cubed. Make sure you use parentheses. Minus 4x squared plus 3. We're going to divide by x minus 2. Now in y2, I'm going to put in what we found the EDA was. 2x squared. And make sure you put your divided by symbol, not multiply, like I did. There we go. Okay, let's graph it. So in y1, you're going to see your original graph. And I might adjust my window a little bit. And in y2, you're going to see your asymptote. Let's see how it looks.
What did you plug in for y2 again?
2x squared. Okay, so that line in red, you know what, I could even make it dotted so we remember it's an asymptote. You don't have to make it dotted, but I'll make it dotted. There we go. Let's graph. So what we want to look at and see is if our graph in blue seems to be getting closer and closer to the dotted red line. Let's check it out. Does it look like my graph in blue is getting closer and closer to that dotted red line as I head up and to the left?
Yeah.
Yes, it is. Eventually, it looks like it's right on top of it, but remember that's because the size of the pixels on the screen can only get so small. Now, it's in the shape of a parabola, my asymptote. So this blue graph should continue being a parabola on the other side. If I can't see it, it's because I'm not zoomed out enough. Let's set the Ymax higher. Let's set the Ymax, let's set it higher and lower. Let's go like negative 15, and let's go to positive 25. Because I should see the graph in blue continuing on the other side. It can't connect because there's a vertical asymptote. But now I can see it on the other side. And if I make it bigger, you can see that the graph in blue is getting closer and closer as you head to the left and to the right to that curved asymptote. The other asymptote is a vertical one. And what value would make the denominator 0 in this case? Yep, 2. So there is a vertical asymptote at 2. That's why the parabola can't connect. Because if it tried to connect, you'd have to divide by 0. You can't plug 2 in. And that's our shape. So the point here is I just want you to see that it's getting closer and closer to that red line. This part is just going to continue up like that. And this part is going to continue down like that. So it's like a parabola that's been, it's like if it wanted to connect, you like cut it, and you bent one side down, and you bent the other side up. That's kind of what's happening. Any questions on that? So even though you don't have to sketch one like that by hand, you do need to know how to find the equation of that red curve using long division. Or synthetic.
How do you do that?
So that was our example number 5.
So the equation for that line would be the quotient, the x
It was the quotient we found,
cubed with the remainder of 3.
2x squared.
Oh yes, sorry. Yeah. And the other question I had, when you're graphing and you plug it into the calculator, why does it change what the graph looks like depending what the parentheses are on?
Why?
Yeah.
Order of operations.
Okay, so when you have something like the problem we just did, it would be the x minus 2 that's in parentheses, right?
I think I put the entire numerator in parentheses, and I put the denominator in parentheses.
How do you know when you're supposed to use it? Should you just always use parentheses?
When you're typing a fraction in that has variables in the numerator and denominator, yes.
Okay.
Because a fraction bar is a grouping symbol. Just like parentheses are a grouping symbol, so is a fraction bar. Like if you had all this, and then you had 8 cubed minus 4 times 5 plus 6. If you're doing this arithmetic problem, because you have a fraction bar in there, that means you should do the entire top first and then do the entire bottom second.
And then for that, those points that you plotted, so that top equation is our original equation, and the y2 is the end behavior asymptote, and you use those two plots to find the slant asymptote?
Nope, haven't done anything with a slant yet.
Oh,
I answered a question about that earlier, but we haven't talked anything about slants.
so what did you just find?
I just graphed the EDA to basically show that it looks like it is the asymptote.
Okay.
To show that my graph is getting closer and closer and closer to it.
So
That's all I wanted to show.
That whole graphing process is just to support that.
Yeah.
that equation.
To make it, to check if that answer we got seemed reasonable, and based on the graph we had, it looked very reasonable, that it was getting closer and closer. Yeah. Now, if I had a parabola that looked different, and the parabola for my asymptote wasn't anywhere near this blue thing, then I would say, well, I probably have the wrong equation for the parabola. It has to be getting closer and closer to it. And that's exactly what's happening there. Now, does the blue and the red ever really touch? No, they never touch. All right, so let's try sketching this one. Now, at first, it looks like it's a little bit more complicated, but this is actually going to be simpler than the last one. And we're going to sketch it by hand. Before we do anything, what's the degree in the top? Yep. And the degree in the bottom? 2. That's better than the last one because now they're only 1 apart. So your asymptote here is going to be a degree 1, which we just talked about is a line, but not necessarily horizontal. It's going to be on a slant. Okay, so to find the vertical asymptotes, what do we focus on to find vertical asymptotes? The numerator or the denominator? Caleb? The denominator. And what do we specifically want to know about the denominator? Yes.
Okay. You want to know what you put in to get 0?
Right. We want to know what we would fill into the denominator to get 0. This part is the same as yesterday. So what should I do with the denominator to make it easier to figure out what I would fill in to make it 0? It's kind of hard for me to just look at x squared plus 2x minus 3. Yep.
Right here.
We're going to factor it. So that's going to factor as x. We're going to need a minus 2. No, we need a minus 3 and a 1. One of them will be plus, one will be minus. And I would make the 3 the plus. And the 1 the minus. Yep, that's how it factors. Okay, so where, what do they want to know? Determine vertical asymptotes. Okay, how many vertical asymptotes does this one have? Yep. 2. And where are they?
One's at positive 1.
Okay.
And then one's at negative 3.
Positive 1 and negative 3. Put those in. Positive 1. Negative 3. And now, there's one other asymptote we have to find, and that's the EVA. When you're doing a problem where the degree in the top is larger than the bottom, you do not have horizontal asymptotes. Horizontal asymptotes only exist for the kind of problems we did yesterday. They will never happen when the degree in the top is larger. What will happen instead? Well, you get a parabola asymptote. Depends on how much larger the top is than the bottom. Okay, so how do we find the EVA? Yep. Division. Can I use synthetic division this time? Denominator is way too complicated for synthetic division. So we're going to do x squared plus 2x minus 3. We're going to divide that into 2x cubed plus 7x squared. You know what? I'm just going to do it on a separate piece so I have more space. If you don't already have a graph drawn, you probably have more space than I do. Let's do that. Paste it. Okay, and can somebody tell me what's the rest of it that goes underneath?
I have 2x to the third plus 7x to the second.
2x to the third, 7x to the second, minus 1. Okay. Oh, minus 4? Okay. So because we don't have an x term in there, we need to put the 0 in for that. Eli, what do I get if I divide x squared into 2x cubed?
You get 2x.
2x. Now, multiply that back out. And this is how we do long division. Multiply back out. So 2x times x squared is 2x cubed. Alexis, what's 2x times 2x? 4x squared. Okay. And Quinn, 2x times negative 3?
Negative 6.
Perfect. And does anyone remember what we do with these columns? With synthetic division, we add. But with this, we're going to subtract. 2x cubed minus 2x cubed is gone. What's 7x squared minus 4x squared? 3x squared. 0x minus 6x. Yeah.
Plus 6x.
Plus 6x. And bring down your 4. Now let's keep in mind, what are we interested in here? We're trying to find the EDA. So all we want to know is the quotient. I don't care about the remainder. So once I get the quotient, I'm going to stop. So we're about to get the quotient right now. What do you get if you divide x squared into 3x squared? Yeah? 3. Done. That's your quotient. If you want the remainder, multiply the 3 back out, do all the subtractions. And that is your EDA. 2x plus 3. Okay, in this case, is that an asymptote that's going to curve if I draw 2x plus 3? No, it's going to be a straight line, but it's going to be on a slant. So it's going to be up 3, and my slope is 2. So up 2, right 1. And I'll just do that a few times to fill my graph paper. And then I'll draw in that red line. So that is my asymptote. So it's kind of like what we did yesterday, where you get 6 sections. Yesterday it looked more like this. So you get 1, 2, 3, 4, 5, 6. And we ended up drawing in 3 of them. That's exactly the same thing that's going to happen here. We still have 6. We're going to draw in 3 of them, except the horizontal has been turned at an angle. So from here, we do the same exact thing we did yesterday. Use the calculator, plot some points, start near the asymptotes, and then plot some points in each section. All right, so let's did I type this in yet? I don't think so. No, I gotta type it in. All right, so it's 2x cubed. I can use some of what I already have. Plus 7x squared minus 4. The bottom is totally different. So x squared plus 2x minus 3. Right, let's put in the, well, we can put the EDA in after if we want, see what it looks like. All right, my first vertical asymptote was 1. Somebody give me a value a little bit smaller than 1. Yep.
0.99.
Sorry, 0.99. Okay, now I need a value a little larger than 1. Yep.
1.001.
Perfect. All right, that covers that one. Let's go to the other asymptote. -3. What's a value that's a little bit smaller than -3? So in other words, to the left of it, just past it. Sure, -3.001. All right, now I need a value bigger, just a little bit bigger than -3. Lucas?
-2.999.
Sure, -2.999. All right, let's plot those 4 points. So just before 1, we're down very low. Just after the number 1, we're up very high. So after the number 1, up high. Before the number 1, down low. Okay. Just after -3, we're up very high. And this one looks like I plugged in -3, but I really didn't. Plugged in -2.999, it just rounds it. So just to the right of -3, we're down at -12,000. So very, very low. All right, let's check out more what's happening in between these two. Then we'll check out to the left, and then we'll do to the right. What's a good x value that's between those two vertical asymptotes? Yeah?
Sorry, can you just backtrack for 1 second? How do you graph those numbers if they're so off the charts?
I just go down as low as I can on my graph paper and up as high as
So
I
it's
can.
just an estimate?
Right, because it's just telling me a direction of the curve. That's all I'm looking for. Which way is this graph going to curve? Down or up? So what's a good value between my two asymptotes? About, right? A value between my asymptotes? 1? Well, we could try 1, but I get an error because that is my asymptote.
Oh, like -2.
So we could do -2. So we're at -2, comma -2.6. So -12.6. Okay, right about there. What's another good value between? Yep.
-1.
-1, which actually I don't have. -1, -1/4. So -1, -1/4. I'd say another good one would be 0. 0, 1.3. Okay. I think I got enough points in the middle. So what's happening? Staying very close. Curving through all these points. And then coming back down because it's got to go through this other point that we had over there. So there's your middle. All right, what would be a good x value to see what's happening over in that section? Yeah?
86.
All right, so let's try -1, 2, 3, 4, 5, 6. Okay, so -6, just barely on my graph, but I can do it. -6, -8.8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8.8. I think I drew my line off a little bit here. Should be more like that. Okay, so -6, almost -9. Now, I know I only have 2 points in here. If you want to do one more, I would say -4 would be a good one. -4, -4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's good enough. So have your line come down. And remember, it's going to go through here and here. So it's going to come down. And then it's going to have to curve. It's the only way it can go through those two other points. So there's your left section. And the right section, well, I already got a point here. And I know that it can't cross those dotted lines. So it's probably going to be trapped inside that V between the vertical and the slant. What would be a good X value to see what's happening right inside there? Yep. Yeah, 2 would be a good one. We may have to do like 2.5 to get another one, but let's start with 2. 2, 8. Okay, I can do that. 2, 3, 4, 5, 6, 7, 8. All right, I would do, let's do 2.5 and just see what's happening. All right, 2.5, it's up a little bit. So 2.5 is 8.6. All right, so I can kind of see what's happening. All those points have to connect. So it's going to look something like this. And that's what's happening in your 3 sections. All right, let's do zoom 6. Keep in mind, if you do a zoom 6, you're just barely going to see this top section. You're going to see a very, very small part of it. So zoom 6 might not be the best window. But I think you should see the part on the left. There's that. Part in the middle. Yep. And then you're just seeing a very small part of that shape right up in there. So perfect. That's your sketch. Yes?
So I'm very confused because my graph just kind of cuts off. It doesn't look like that in the slightest. I think I plotted it the same way you did, but mine is not like that.
And you typed in exactly that for your Y1?
Well, I also put the what's it called? The Hager asymptote.
Okay, yeah, you don't need to put that in. You could, if you did, it would just look like this.
Did that mess it up?
No, it would just look like a line cutting up through like that.
Yeah, mine just cuts off. I'm pretty sure I put it in.
If you see quit app in the top right, I would do that for some reason in order to get it to look correct, and now that doesn't show up.
Quit app.
Yeah. If you go to y equals.
So you have a newer one than she does. You have the TI-84 CE. She has a TI-84 Plus.
Yeah,
So I might have to take a look at it and see. But this one had 2 verticals and a slant. When you have 2 verticals, it's a little more complicated because you're going to get those 3 sections. If you only had 1 vertical and a slant, you could get a shape that looks like that. That's a little easier. And that type of graph generally looks something like this. That's what the shape looks like with 1 vertical and a slant. But 2 verticals, it does make it a little bit more complicated. But just use your calculator and plot as many points as you need to. But it's very important you get those vertical and slant asymptotes correct. And speaking of slant asymptote, that's the name of what we just did. And I already kind of told you guys that. So as far as sketching by hand, you don't have to sketch an asymptote that curves by hand. You should be able to sketch the slant that I just did. I still might ask you to find an asymptote that curves, but just not sketch it. You just have to find it. Okay. Any question on that? Okay. So that's part 2, 4.2. So there's not a lot of questions in the homework. It's mostly sketching. And those are the questions. Let me just double check. And just skip 55. We can skip 55. Okay, so it's 40, 41, 45 to 47, and 51.
No, because I accidentally deleted the whole thing and now I don't want to restart it. I just want